A black hole has an edge, invisible yet deadly. This is the event horizon, and it's stranger than you think. The discovery of general relativity. An event horizon is a boundary in space-time where the escape velocity equals the speed of light. That single line contains a huge amount of physics because escape velocity is not just a number attached to rockets and planets, but a direct consequence of how mass curves space-time and when the curvature becomes extreme enough that even light cannot climb back out. A region forms from which no signal, no particle, no radiation can return to distant observers. The important clarification must come immediately. The event horizon is not a surface in the ordinary sense. It is not a physical wall, and it is not made of matter. It is a geometric boundary defined by the structure of space-time itself, meaning that nothing locally marks its presence as a material edge. Yet globally, it separates events that can influence the outside universe from those that cannot. The idea emerged from the field equations published by Albert Einstein. In November 1915, in a lecture hall in Berlin, Albert Einstein stood before the Prussian Academy of Sciences and presented a set of equations that changed how we understand the universe. He did not announce the discovery of black holes. He did not speak about event horizons. He did not describe objects that trap light. What he presented was something more basic and more powerful. He presented a new theory of gravity called general relativity, and in doing so, he replaced a 200-year-old idea about how the universe works. To understand how big this change was, we need to step back into the world before 1915. For over 2 centuries, gravity meant one thing: a force. Isaac Newton had shown that every mass pulls on every other mass. The force gets stronger when objects are heavier and weaker when they are farther apart. This simple rule explained falling apples, ocean tides, the moon's orbit, and the motion of the planets. It worked so well that no one doubted it. Space was seen as an empty stage. Time was seen as a steady clock ticking the same everywhere. Gravity acted across that stage like an invisible rope pulling objects together. Einstein looked at that picture and saw cracks. He was not trying to invent black holes. He was trying to fix small problems that did not fit Newton's rules. One of those problems was the orbit of Mercury. The planet's path around the Sun shifted slightly over time in a way Newton's equations could not fully explain. The difference was small, but it was real. Instead of adjusting Newton's force with a small correction, Einstein asked a deeper question. What if gravity is not a force at all? He had already shaken physics in 1905 with special relativity, which showed that space and time are linked and that the speed of light is constant for all observers. That idea alone changed how we measure time and distance. Clocks moving at high speeds tick slower. Rulers moving at high speeds shrink. Space and time were no longer fixed. They depended on motion. But special relativity did not include gravity. It worked only for constant speeds, not acceleration. Einstein knew that gravity involves acceleration. If you drop a ball, it speeds up. If you stand on Earth, you feel weight because you are pushed upward by the ground. He spent almost 10 years trying to combine gravity with the ideas of curved space and flexible time. The key thought that guided him was simple, but powerful. Imagine you are inside a closed elevator. If the elevator is floating in deep space far from any planet and it suddenly accelerates upward, you will feel pressed to the floor. If instead the elevator is standing still on Earth, you will feel the same pressure on your feet. From inside the box, without looking outside, you cannot tell the difference. Acceleration and gravity feel the same. This idea is called the equivalence principle. From that single idea, Einstein made a leap. If acceleration can change how objects move, and if gravity feels like acceleration, then gravity must also change how objects move in a similar way. But instead of thinking of gravity as a push or pull, he began thinking of it as something built into the shape of space and time. He imagined space and time not as separate things, but as one combined structure called spacetime. Picture it not as a flat, empty box, but as a flexible fabric. When nothing is there, this fabric is smooth. When mass or energy is placed on it, the fabric bends. Objects moving nearby follow the curves in that fabric. They are not being pulled by a force in the old sense. They are simply following the natural paths in curved spacetime. This was not just an image. Einstein worked out exact equations that describe this bending. They are complex and involve advanced math, but the idea behind them is clear. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. When a planet orbits the Sun in this picture, it is not being dragged by a force. The Sun curves spacetime around it. The planet moves forward in time, following the straightest possible path in that curved geometry. In curved space, the straightest path can look curved from the outside. That is why orbits form. In November 1915, Einstein presented the final version of these equations. They connect the curvature of spacetime to the energy and mass inside it. The left side of the equation describes geometry. The right side describes matter and energy. The two are linked directly. It is a relationship between shape and substance. At that moment, no one spoke about black holes. The equations were new and difficult. Most physicists were still trying to understand what they meant. Einstein himself focused first on testing whether his theory matched known facts. When he applied his equations to Mercury's orbit, the missing shift was explained perfectly. That alone was a major success. Soon after, another prediction was tested. If gravity bends spacetime, then light should follow curved paths near massive objects. In 1919, during a solar eclipse, astronomers measured the positions of stars near the Sun. Their light was slightly bent as it passed close to the Sun's mass. The amount of bending matched Einstein's prediction. The result made headlines around the world. Einstein became famous almost overnight. But even with this success, the deeper consequences of the equations were still hidden. General relativity said that space can stretch and shrink. It said that time runs slower near massive objects. A clock on a mountain ticks slightly faster than a clock at sea level because Earth's gravity is weaker higher up. These effects are tiny on Earth but real and measurable. Modern GPS satellites must adjust for this time difference, or their signals would drift. All of this comes directly from Einstein's equations. What no one fully explored yet in 1915 was what happens when mass becomes extremely dense. The equations do not limit how strong curvature can become. If more mass is packed into a smaller region, space-time bends more sharply. If enough mass is squeezed into a small enough space, the bending becomes extreme. Einstein did not predict specific objects that trap light. He did not announce the existence of a boundary where escape becomes impossible. But his equations allowed such solutions. They did not forbid them. They did not break under extreme gravity. They simply described what the geometry would look like. At this stage in history, there were no telescopes powerful enough to see distant galaxies clearly. There were no X-ray detectors in orbit. There were no radio arrays imaging distant cosmic objects. Physics was driven mostly by theory and small laboratory experiments. The idea that a star could collapse into something so dense that even light cannot escape was far from most scientists' minds. Einstein himself believed that nature would avoid extreme singular behavior. He trusted that some physical process would stop total collapse before space-time became too distorted. The equations were powerful, but their most extreme solutions seemed unrealistic at the time. Still, the seeds were planted. General relativity changed the foundation of physics. It removed gravity as a basic force and replaced it with geometry. It made space dynamic, it made time flexible, it connected motion to curvature, and most importantly, it provided a tool that could be applied to any distribution of mass and energy, from small stars to the entire universe. The impact of this shift cannot be overstated. Once gravity became geometry, new questions opened. How curved can space-time become? Is there a limit? What happens when a massive star runs out of fuel? What does the geometry look like near extremely dense matter? In 1915, these questions were not yet answered. The theory existed, but its extreme predictions had not been explored. The language of curved space-time was new. Physicists were still learning how to solve the equations in simple cases. Einstein had provided the framework. Others would soon begin testing its edges. At this moment in history, the story is pure theory. A man working through mathematics reshapes our picture of reality. There are no black holes yet. There is no event horizon named or described. There are only equations that connect mass to curvature and curvature to motion. Gravity is no longer a pull across empty space. It is the shape of space-time itself. And hidden inside those equations, waiting to be uncovered, is the possibility that if space-time curves enough, there will be a boundary beyond which no path leads back out. But in 1915, that idea has not yet stepped into the light. There is only a new vision of the universe, written in symbols, quiet but powerful, ready to reveal consequences that even Einstein did not fully expect. Schwarzschild's solution, 1916. In 1916, only months after Albert Einstein completed general relativity, a German physicist named Carl Schwarzschild accomplished something extraordinary under conditions that make the story even more intense. Schwarzschild was not sitting in a quiet university office when he solved Einstein's equations. He was serving in the German army on the Eastern Front during World War I, surrounded by artillery fire, harsh weather, and the daily uncertainty of war. In the middle of that chaos, using paper, pencil, and deep mathematical focus, he found the first exact solution to Einstein's brand new theory. Einstein's equations were not simple formulas that could be solved easily. They were complex nonlinear equations that described how space-time curves in response to mass and energy. Most physicists at the time did not even know where to begin with them. The equations allowed countless possible geometries depending on how matter was arranged, and finding even one exact solution required both skill and creativity. Schwarzschild chose the simplest physical case imaginable, a single, perfectly spherical mass that does not rotate and does not change over time. He asked a clear question. If you place a spherical mass in empty space, what does space-time look like around it? By focusing on symmetry, Schwarzschild reduced the complexity of the equations. A perfect sphere looks the same from every direction, which means the curvature around it must also follow that symmetry. He worked through the tensor mathematics carefully and arrived at a precise expression for the geometry of space-time outside that mass. This result is now called the Schwarzschild metric, and it remains one of the most important solutions in all of physics. What Schwarzschild discovered was that space-time around a spherical mass is not only curved in space, but also in time. The geometry shows that clocks closer to the mass tick more slowly than clocks far away. It also shows that distances are stretched in the radial direction near the mass. These predictions were direct consequences of Einstein's theory, but Schwarzschild's solution made them concrete and measurable. Then came the surprising part. In his equations, a special radius appeared, a distance from the center of the mass where the mathematical expression seemed to break down. This radius is now known as the Schwarzschild radius, written as R sub s equals 2gm over c squared. In this formula is the gravitational constant, is the mass of the object, and is the speed of light. The formula shows something remarkable. The critical radius depends only on the mass. If you know how heavy an object is, you can calculate the radius at which this strange behavior appears. For ordinary objects like Earth or the Sun, this radius is extremely small compared to their actual size. If Earth were compressed to about the size of a marble, it would reach its Schwarzschild radius. If the Sun was squeezed down to a sphere about 3 kilometers across, it would reach its Schwarzschild radius. In 1916, no one believed such compression could actually happen in nature, but the mathematics clearly allowed it. At this special radius, something dramatic occurs in the equations describing time and space. The factor that controls how time flows relative to a distant observer becomes zero. That means that, from far away, a clock placed exactly at that radius would appear to stop ticking. Light emitted from that radius would be stretched infinitely, losing all its energy as it climbs out of the gravitational field. The escape velocity at that distance equals the speed of light. Anything inside that radius would require traveling faster than light to escape, and since relativity forbids faster than light motion, escape becomes impossible. Schwarzschild himself did not describe this boundary as an event horizon, because that term did not yet exist. He simply identified the mathematical feature. At first glance, it looked like a true physical singularity, as if space-time itself became infinitely distorted there. However, the deeper truth was more subtle. The apparent breakdown came from the coordinates used to describe space-time. It was similar to how longitude lines meet at the North Pole on a globe, making the coordinate system behave strangely there, even though the surface itself is smooth. Later, mathematicians would introduce new coordinate systems that pass smoothly through this radius without any infinite values appearing in the geometry. Those new coordinates revealed that the Schwarzschild radius is not a physical tear in space-time, but a boundary where the nature of time and space shifts in a fundamental way. However, in 1916, that clarity did not yet exist. The equation simply showed that something special happens at that radius. What makes Schwarzschild's work so powerful is that it turned Einstein's general idea into a specific, exact description. Instead of speaking broadly about curved spacetime, physicists now had a concrete example of curvature around a mass. They could calculate how much light bends near the sun. They could calculate how much time slows down near a massive object, and they could explore what happens if mass is concentrated more and more tightly. The Schwarzschild solution applies only outside the mass, meaning it describes the region of empty space surrounding a spherical object. It does not describe what happens inside the mass itself. That limitation was important. The solution did not initially prove that a star could shrink inside its Schwarzschild radius. It only showed what the geometry would look like if such a thing occurred. Even so, the appearance of this special radius planted a seed. The mathematics suggested that if enough mass were packed within that critical distance, spacetime would curve so steeply that every path leads inward. Light emitted inside would never reach distant observers. Signals would be trapped. The geometry would form a one-way boundary. Schwarzschild sent his solution to Einstein in a letter from the front. Einstein was impressed by the speed and skill with which Schwarzschild had solved the equations. Tragically, Schwarzschild fell ill with a rare autoimmune disease while serving in the army and died later in 1916 at the age of 42. His exact solution, completed under the stress of war, became a foundation stone for everything that followed in black hole physics. At the time, most scientists saw the Schwarzschild radius as a mathematical curiosity rather than a physical prediction. The idea of compressing a star to such a small size seemed unrealistic. No known process could achieve that level of collapse, at least according to early 20th century knowledge. The focus remained on weaker gravitational fields where predictions could be tested. However, the formula was simple and clear. It linked mass directly to a critical size. It showed that there is nothing magical about the radius itself, except the amount of mass packed within it. Any mass, if squeezed tightly enough, would have such a radius. This universality hinted that the phenomenon was not tied to exotic matter, but to geometry alone. The deeper implication was this: the structure of spacetime contains built-in limits. As mass increases or as volume decreases, curvature grows stronger. If curvature reaches a certain level, a boundary appears where escape velocity equals the speed of light. That boundary is not imposed by new physics. It arises directly from Einstein's equations, combined with symmetry. Schwarzschild's work marked the first time this boundary appeared clearly in mathematics. Although its meaning was debated and misunderstood for decades, the critical radius remained in the equations, waiting for physicists to interpret it correctly. The discovery was quiet but profound. In the trenches of war, using the tools of pure thought, Schwarzschild uncovered the geometric condition that would later define the edge of a black hole. At this stage in history, there was still no confirmed object in the sky matching this description. There were no X-ray sources identified as collapsed stars. There were no radio signals tracing matter falling into invisible wells. There was only a formula connecting mass and radius, and a strange mathematical feature that appeared when the two reached a certain balance. The Schwarzschild solution did not announce the existence of black holes in 1916, but it provided the precise geometry that would later describe them. It revealed that Einstein's theory allows a region of spacetime where escape becomes impossible. It introduced a radius that depends only on mass. It showed that time slows and light redshifts near that boundary. And it did all of this with exact mathematics that still stands unchanged today. What began as an attempt to understand the curvature around a simple sphere became the doorway to understanding some of the most extreme objects in the universe. The equation was clear. The radius was defined. The geometry was written down. The consequences would take decades to fully unfold. The Misinterpretation era, 1916 to 1950s. After Carl Schwarzschild published his exact solution in 1916, the equations were clear, but their meaning was not. And for decades, physicists struggled to understand what the strange radius in the mathematics actually represented. Because at that location, the formulas seemed to explode into infinities, and the geometry appeared to break apart. The Schwarzschild radius looked like a physical boundary where time stopped and space became undefined. And since infinities in physics often signal something impossible or unphysical, many scientists assumed that the solution must be hiding a flaw rather than revealing a real feature of nature. The idea that a star could shrink so much that light itself could not escape sounded extreme and disconnected from the stars observed in the sky. So most researchers treated the result as a mathematical curiosity instead of a physical prediction. Albert Einstein himself did not believe that nature would allow such an object to form. Although his equations permitted the existence of the Schwarzschild radius, he suspected that real physical processes would prevent a star from collapsing that far. In 1939, Einstein even published a paper arguing that a cluster of particles in circular orbits would never collapse to the point of forming what we now call a black hole, because he believed stability would arise before such an extreme state was reached. His reasoning was based on the physics understood at the time, when nuclear forces and quantum effects were still being explored, and when the idea of matter compressing beyond atomic or even nuclear limits seemed unrealistic. Einstein trusted that some mechanism in nature would intervene before gravity pushed matter into a state where space-time curved without limit. Part of the confusion during this period came from how the Schwarzschild solution was written. The original coordinates used to describe space-time made the metric appear singular at the Schwarzschild radius, meaning certain mathematical terms became infinite or zero in a way that suggested something physically dramatic was happening. In reality, the problem was not with space-time itself, but with the coordinate system chosen to describe it. This is similar to how the longitude lines on Earth meet at the North Pole, making longitude undefined at that exact point, even though the surface of the Earth is smooth and well behaved there. The singularity at the Schwarzschild radius was a coordinate singularity, not a physical singularity, but that distinction was not immediately understood. Because the mathematics seemed to fail at that radius, many physicists assumed the solution could not represent a real object. They believed the singular behavior meant the theory itself might break down before reaching that point. At the time, the language of curved spacetime was still new, and the tools needed to analyze global geometry were not fully developed. The deeper understanding that different coordinate systems can describe the same physical reality in different ways took time to mature. Without that understanding, the Schwarzschild radius looked like a place where physics simply stopped making sense. Another reason for doubt was the absence of observational evidence. In the early 20th century, astronomy was limited by the power of optical telescopes. Neutron stars had not yet been confirmed. The internal structure of stars was not completely understood. There was no known mechanism that could compress matter beyond the density of atoms, let alone beyond the density of atomic nuclei. Without a clear physical path leading to such collapse, the Schwarzschild radius remained an abstract idea. It existed in equations, but not in telescopes. The dominant belief during this era was that stars achieve balance between inward gravitational pull and outward pressure from heat generated by nuclear reactions. When a star burns fuel, radiation pressure pushes outward and gravity pulls inward, and as long as those two forces balance, the star remains stable. Even when fuel runs low, scientists believed new forms of pressure would appear to resist further collapse. First, there is thermal pressure from hot gas. Then there is electron degeneracy pressure, a quantum effect that prevents electrons from being squeezed into the same state. Later, neutron degeneracy pressure was proposed as a force that could resist even stronger compression. Each time gravity seemed ready to win, physics provided another form of resistance. Because of these ideas, most researchers believed that collapse would always stop before reaching the Schwarzschild radius. The concept of a complete gravitational collapse into a region from which nothing escapes felt like an extreme mathematical extrapolation rather than a real astrophysical process. Even Einstein favored this view. He trusted that nature was orderly and would not allow such runaway collapse. His hesitation influenced others, because if the creator of general relativity doubted the physical reality of such objects, it was easy for the community to remain skeptical. During the 1920s and 1930s, physicists were also deeply focused on quantum mechanics, which was developing rapidly and reshaping the understanding of atoms and particles. The attention of the scientific world shifted towards subatomic physics, leaving the extreme predictions of general relativity somewhat neglected. Gravity was seen as a weak force compared to electromagnetism or nuclear forces, and its strange mathematical features were not urgent problems demanding immediate resolution. As a result, the question of whether the Schwarzschild radius represented a real boundary remained unsettled. The misunderstanding of coordinate singularities played a central role in prolonging the confusion. It took decades before mathematicians developed better tools for analyzing spacetime geometry in a coordinate-independent way. Eventually, alternative coordinate systems were introduced that removed the artificial singular behavior at the Schwarzschild radius. These new descriptions showed that spacetime remained smooth at that boundary, and that an observer falling inward would not encounter infinite forces there. However, this clarity did not come immediately. For many years, the apparent infinity in the equations reinforced the belief that something unphysical was occurring. At the same time, the idea of a singularity at the center of the solution, where curvature becomes truly infinite, added to the discomfort. A true singularity is different from a coordinate artifact, because it represents a point where the curvature of spacetime itself becomes infinite, and the known laws of physics break down. The existence of such a point seemed unacceptable to many scientists, who believed that a complete theory of nature should avoid infinities. This philosophical discomfort, combined with the mathematical confusion, strengthened the view that real stars would never collapse so completely. The term black hole did not yet exist during this era, and the concept did not have a clear identity. The Schwarzschild radius was sometimes referred to as a Schwarzschild singularity, which made it sound like a flaw rather than a feature. Without a clear physical picture, the idea remained in the background of theoretical discussions. It was known, but not embraced. The belief that nature would prevent collapse was not unreasonable, given the knowledge of the time. The discovery of white dwarfs and later neutron stars showed that matter can resist gravity through quantum effects. These discoveries supported the idea that new forms of pressure emerge at high densities, stopping collapse before extreme curvature forms. The question was whether there exists a limit beyond which even these pressures fail. That answer had not yet been fully explored. Throughout the 1940s and into the 1950s, general relativity remained mathematically respected, but physically underused. Many physicists considered it elegant but impractical, useful for explaining Mercury's orbit and light bending, but not central to mainstream physics. The extreme solutions were still seen as exotic edge cases. The tools needed to study gravitational collapse in full detail had not yet been applied. This period, stretching from 1916 to the mid-20th century, can be understood as a long pause between discovery and acceptance. The equations allowed for the existence of a boundary where escape velocity equals the speed of light, but most scientists believed such a boundary would never form in reality. Einstein himself doubted it. The coordinate confusion made the boundary look unphysical. The lack of observational evidence left it unsupported. And the belief in stabilizing pressures encouraged the idea that collapse would always stop in time. The mathematics had spoken clearly, but interpretation lagged behind. The Schwarzschild radius remained in the equations, quiet and unresolved, waiting for a deeper analysis of gravitational collapse to show whether nature truly allows matter to pass that critical point. Oppenheimer and gravitational collapse, 1939. By the late 1930s, the idea of extreme gravitational collapse was still surrounded by doubt. And although the equations of general relativity allowed matter to compress beyond the Schwarzschild radius, most physicists believed that some form of pressure would always stop the collapse before that point was reached. White dwarfs had already been discovered, and they were supported not by heat, but by electron degeneracy pressure, a quantum effect that arises because electrons cannot occupy the same quantum state. Then neutron stars were proposed, supported by neutron degeneracy pressure, which is even stronger. It seemed reasonable to assume that nature had built-in limits, layers of resistance that would activate one after another as gravity squeezed matter tighter and tighter. The question was simple but profound. What happens if a star is so massive that even neutron degeneracy pressure is not enough? In 1939, two physicists at the University of California, Berkeley, decided to answer that question directly using Einstein's equations. Their names were J. Robert Oppenheimer and Hartland Snyder. Oppenheimer would later become widely known for his role in the Manhattan Project, but in 1939 he was a theoretical physicist deeply interested in astrophysics and the behavior of matter under extreme conditions. Together with Snyder, he set out to examine what general relativity actually predicts for a massive star that has exhausted all sources of pressure capable of resisting gravity. They did not approach the problem with vague assumptions. They constructed a clear, idealized model. They imagined a perfectly spherical star made of pressureless dust, meaning matter with mass, but no internal pressure resisting compression. This simplification allowed them to focus purely on gravity without adding complications from complex equations of state. The goal was not to describe every detail of a real star, but to determine whether gravitational collapse could, in principle, continue without limit under Einstein's theory. Using the Schwarzschild solution to describe the spacetime outside the collapsing star and solving the equations for the interior, they tracked what happens as the star shrinks under its own gravity. What they found was not a temporary instability or a bounce back to equilibrium. The equations showed continuous collapse. Once the star began shrinking and no force remained strong enough to oppose gravity, nothing in general relativity stopped it. the radius of the star decreased steadily, and if its mass was large enough, it eventually passed within its own Schwarzschild radius. This was the turning point. When the surface of the star crossed the critical radius, something dramatic occurred in the geometry. From the perspective of an observer far away, the surface of the star appeared to approach the Schwarzschild radius more and more slowly. Light emitted from the surface became increasingly redshifted, losing energy as it climbed out of the deep gravitational well. The signals took longer and longer to arrive. To the distant observer, the collapse seemed to freeze at the boundary. The star's surface never appeared to cross it. Instead, it faded and dimmed, its light stretched toward infinite wavelength. However, from the perspective of matter falling inward with the collapsing star, the story was very different. Oppenheimer and Snyder calculated the proper time experienced by the infalling material and found that the collapse to zero radius occurs in a finite amount of time. There is no infinite delay from the viewpoint of the star itself. The material does not hover at the boundary. It passes through the Schwarzschild radius and continues inward toward a state of extreme density. This dual description was entirely consistent with general relativity. The difference arises because time flows differently in strong gravitational fields. Clocks near the collapsing surface tick more slowly relative to clocks far away. As the surface approaches the Schwarzschild radius, time dilation becomes extreme. For a distant observer, the slowing becomes so severe that the crossing appears to take forever. But for the collapsing matter, its own clock runs normally, and the crossing happens without any sudden barrier. What made this work revolutionary was not that it introduced new equations, but that it applied Einstein's existing equations to a realistic astrophysical scenario. It showed that if a star is massive enough and no pressure remains to stop gravity, collapse is unavoidable. There is no built-in safeguard in general relativity that halts the process at neutron density. If the mass exceeds a certain limit, neutron degeneracy pressure fails. The inward pull of gravity continues to strengthen as the radius shrinks. The curvature of spacetime intensifies. The Schwarzschild radius is eventually reached and passed. At that moment, the boundary described decades earlier by Schwarzschild stopped being an abstract mathematical feature and became a real outcome of stellar evolution in the equations. The event horizon, though not yet called by that name, became inevitable in the mathematics of gravitational collapse. Oppenheimer and Snyder were careful in their conclusions. They did not use dramatic language. They described the final state as continued contraction toward a singular state of infinite density. They acknowledged the strange behavior seen by distant observers, where the surface appears to freeze and its light fades away. But they made it clear that according to the equations, nothing prevents the star from collapsing beyond the critical radius. This result directly challenged the earlier belief that nature would always prevent total collapse. It showed that the protective layers of quantum pressure have limits. Electron degeneracy pressure can support white dwarfs only up to about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. Neutron degeneracy pressure can support neutron stars only up to a few solar masses. Beyond those limits, no known force can stop gravity within the framework of general relativity. In their model, once the collapse began, it accelerated. The curvature grew stronger. The escape velocity at the surface increased. Eventually, the escape velocity equaled the speed of light. That was not a symbolic threshold. It was a direct consequence of the geometry described by the Schwarzschild solution. When the surface crossed that radius, all future directed paths within the star led inward. Light emitted after that point could never reach distant space. The boundary formed naturally from the equations. Despite the power of their analysis, the 1939 paper did not immediately transform physics. The world was on the edge of World War II, and attention soon shifted away from theoretical astrophysics. Oppenheimer himself would soon become deeply involved in nuclear weapons research. the idea of continued gravitational collapse faded into the background once again. However, the mathematical result remained. It demonstrated that the Schwarzschild radius is not merely a coordinate illusion or an unreachable limit. It is a real boundary that forms when enough mass is compressed within its critical radius. The event horizon emerges as a natural feature of spacetime when collapse proceeds without resistance. The importance of this work lies in its clarity. It removed the belief that collapse must always stop. It showed that under certain conditions, collapse continues beyond neutron degeneracy. It linked stellar evolution to the extreme predictions of general relativity. It revealed that the formation of a horizon does not require exotic new physics, only sufficient mass and the absence of opposing pressure. The equations predicted that once the surface of a star passes the Schwarzschild radius, no signal from that surface can ever reach the outside universe again. The geometry traps light. Time dilation grows without bound from the viewpoint of distant observers. The interior region becomes causally disconnected from the outside. This is not because of a solid shell or physical wall, but because the structure of space-time itself redirects all possible paths inward. By the end of their calculation, Oppenheimer and Snyder had shown that the event horizon is not optional if certain mass limits are exceeded. It is built into the geometry. If gravity is allowed to dominate completely, the horizon forms inevitably. Their work marked the first clear demonstration that black hole formation is not a fantasy, but a logical outcome of Einstein's theory when applied to massive stars. Although the term black hole would not be introduced until decades later, the essential physics was already present in 1939. The event horizon had moved from speculation to mathematical necessity. In the years that followed, further work would refine the picture and clarify the geometry, but the core idea was established here. A sufficiently massive star, once it exhausts all pressure support, will collapse beyond neutron degeneracy, pass within its Schwarzschild radius, and form a region from which no light can escape. The boundary that earlier seemed mysterious and perhaps unphysical was now anchored to the life cycle of stars. The inevitability lies in the equations. Once the mass is above the stability limit and pressure fails, curvature increases without bound as the radius shrinks. The escape velocity rises steadily until it equals the speed of light. At that exact radius, the event horizon forms. Beyond it, all future paths lead inward. General relativity does not hesitate. It does not introduce a rescue mechanism. It allows collapse to proceed. In 1939, the path from stellar death to horizon formation was laid out step by step in mathematical detail. The result did not yet capture the imagination of the public or dominate astrophysics, but it established something fundamental. The event horizon is not merely a coordinate artifact or a trick of algebra. It is the unavoidable consequence of gravitational collapse in Einstein's theory when mass exceeds the limits set by quantum pressure. The term black hole, naming the unthinkable, 1967. J. Robert Oppenheimer and Hartland Snyder showed that if a star were massive enough, no known physical pressure could halt its collapse once nuclear fuel was exhausted, meaning that the formation of an inescapable boundary was not a speculative fantasy, but a mathematical inevitability embedded in general relativity itself. Yet despite the clarity of the equations, physicists struggled with language, referring to these objects with cumbersome phrases such as gravitationally completely collapsed objects or frozen stars. Terminology that was technically descriptive but conceptually unsatisfying, failing to capture the stark physical reality implied by the mathematics. The turning point came in 1967 when John Archibald Wheeler introduced a term that condensed decades of theoretical confusion into two words that were both simple and scientifically powerful: black hole. Wheeler did not invent the underlying physics, nor did he derive the original solutions, but he recognized that the field needed a unifying conceptual anchor, and in giving the phenomenon a name, he provided exactly that, transforming an awkward technical abstraction into a clearly defined physical entity. The phrase immediately redirected attention toward the defining feature of these objects, which was not the singularity hidden at the center where densities diverge and current theories break down, but rather the boundary surrounding it, the surface in space-time beyond which no signal can escape. This boundary, now universally known as the event horizon, became central to the modern understanding of black holes because it represents a fundamental shift in causal structure rather than merely extreme gravity. Within the framework of general relativity, space-time is not a passive stage, but an active geometry shaped by mass and energy. And when collapse proceeds beyond a critical threshold, the curvature becomes so extreme that all possible future paths inside a certain radius lead inward. Light cones, which define the directions in space-time that light, and therefore information, can travel, tilt progressively toward the center as one approaches this boundary, and once crossed, every future directed trajectory inevitably terminates at the singularity. The event horizon is not a physical membrane made of matter, nor does it exert a tangible force at the moment of crossing, yet it represents an absolute limit to communication, separating regions of the universe that can influence distant observers from those that cannot. Before the term black hole was adopted, much of the discomfort surrounding these objects stemmed from confusion about coordinate singularities, particularly the apparent divergence at the Schwarzschild radius, which earlier generations of physicists mistakenly interpreted as a physical pathology of space-time itself. By the 1950s and 1960s, improved mathematical techniques demonstrated that this divergence was merely a feature of the coordinate system and could be removed by choosing more appropriate coordinates, revealing that the Schwarzschild radius corresponded to a perfectly regular surface in space-time geometry. What remained was not a mathematical illusion, but a genuine causal boundary, and the recognition of this fact shifted the focus of research away from the problematic center and toward the horizon as the defining structural feature. Wheeler's terminology crystallized this shift, making it natural to speak of black holes as objects characterized by horizons rather than singularities. The impact of this naming extended beyond semantics because it accelerated theoretical development at a critical moment in physics. Once black holes were recognized as legitimate physical entities rather than exotic curiosities, researchers systematically classified their possible forms, deriving solutions that described rotating and charge configurations and discovering that, despite their violent origins, black holes are astonishingly simple when viewed from the outside. The external gravitational field of a black hole can be completely described by just three parameters: mass, angular momentum, and electric charge, an insight that Wheeler summarized in his famous remark that black holes have no hair, meaning that all the complex details of the matter that formed them are hidden behind the horizon and inaccessible to external measurement. This simplicity reinforced the importance of the event horizon as the true defining characteristic, because everything that can be observed or measured lies outside it, while everything beyond it is causally disconnected from the rest of the universe. At the same time, observational astronomy was undergoing a transformation that would soon provide compelling evidence that black holes were not merely theoretical constructs. The discovery of quasars in the early 1960s revealed astronomical objects with luminosities so extreme that no conventional stellar mechanism could account for their energy output, and theoretical models increasingly pointed to supermassive black holes accreting matter at the centers of galaxies as the only viable explanation. X-ray observations of binary star systems uncovered compact objects with masses exceeding the theoretical limit for neutron stars, further strengthening the case for the existence of stellar mass black holes. The terminology introduced in 1967 proved essential in unifying these disparate lines of evidence, allowing astrophysicists to speak coherently about a single class of objects whose defining feature was the presence of an event horizon. The concept of the event horizon also reshaped the understanding of time and causality in extreme gravitational fields. To a distant observer, matter falling toward a black hole appears to slow and redshift as it approaches the horizon, asymptotically fading from view as its emitted light becomes increasingly stretched and weakened, creating the impression that the infalling object never quite crosses the boundary. Yet from the perspective of the falling matter itself, the crossing occurs in finite proper time, with no dramatic local signal marking the transition, illustrating the profound relativity of simultaneity and observation embedded in Einstein's theory. This dual description is not contradictory, but reflects the geometric structure of space-time, in which the horizon is defined globally by the paths of light rays extending into the infinite future, rather than by any local measurement. By giving the phenomenon a name, Wheeler did more than simplify language. He provided a conceptual framework that unified theoretical physics and observational astronomy at a moment when both were poised for rapid expansion. The term black hole encapsulated the essential physical property that defines these objects, namely the existence of a region from which no information can escape. And in doing so, it shifted scientific focus toward the study of horizons, thermodynamic properties, quantum effects, and gravitational wave emissions that would dominate research in the decades to follow. What had once been dismissed as a mathematical oddity became one of the central pillars of modern astrophysics, and the clarity of the name played a subtle but crucial role in that transformation. By the end of the 1960s, black holes were no longer theoretical embarrassments lurking in the equations of general relativity, but well-defined physical entities characterized by event horizons that fundamentally alter the causal structure of spacetime, marking a boundary beyond which the universe cannot observe itself. When escape velocity reaches the speed of light. Imagine you are standing on the surface of a planet and you throw a ball straight up. If you throw it softly, it rises and then falls back down. If you throw it harder, it goes higher before gravity pulls it back. But if you could throw it fast enough, it would never come back. It would escape the planet forever. The speed you need to do that is called escape velocity. On Earth, escape velocity is about 11 kilometers per second. Rockets must reach that speed to break free from Earth's gravity. Bigger planets have stronger gravity, so their escape velocity is higher. Smaller objects have lower escape velocity. Now imagine something much more extreme than a planet. Imagine a massive star, many times heavier than our Sun, collapsing under its own gravity after it runs out of fuel. As it shrinks, all its mass gets packed into a smaller and smaller space. Gravity at the surface becomes stronger and stronger. As the star collapses, escape velocity keeps increasing. First, it might be thousands of kilometers per second, then tens of thousands, then hundreds of thousands. There comes a moment when something incredible happens. The escape velocity becomes equal to the speed of light, and nothing can go faster than light. This is not just a rule of technology. It is a rule of nature. According to relativity, the speed of light is the ultimate speed limit of the universe. No signal, no particle, no force can move faster than light. Not even light itself can exceed its own speed. So what happens if escape velocity reaches light speed? It means that even light cannot escape, and if light cannot escape, then nothing can. The radius at which this happens is called the Schwarzschild radius, named after Karl Schwarzschild, who first calculated it in 1916 using Albert Einstein's equations of gravity. If all the mass of an object is compressed inside this radius, a black hole forms. This boundary is what we call the event horizon. But here is the key idea: the event horizon is not a wall. It is not made of matter. It is not a solid shell. It is simply the distance from the center, where escape velocity equals the speed of light. Outside this radius, escape velocity is less than light speed. If you have enough energy, you can still move away. Inside this radius, escape velocity is greater than light speed, and since nothing can move faster than light, escape becomes impossible. Now let's think about this in a deeper way. In everyday life, we think of gravity as a force pulling things inward. But in Einstein's theory, gravity is not really a force. It is the bending of space and time. Massive objects curve space-time around them, and everything moves along those curves. Far from a black hole, space is only slightly curved. You can move in many directions. You can go forward, backward, left, right, up, or down. But as you get closer to the event horizon, space becomes more and more curved inward. Right at the event horizon, the curve becomes so extreme that all possible paths forward lead inward. Inside that radius, every possible future path bends toward the center. It does not matter which way you try to go. It does not matter how powerful your rocket is. The structure of space-time itself is tilted inward. It is like standing in a river that is flowing toward a waterfall. Far upstream, you can swim against the current. Closer to the waterfall, the water moves faster. There is a point where the water flows as fast as you can swim. If you pass that point, no matter how hard you try, the current carries you over the edge. The event horizon is that point in space-time. Outside it, you can still fight the current. Inside it, all roads lead inward. And here is the most important part. Once something crosses this boundary, it cannot send a signal back out. Not because something blocks it, but because there is no path that leads outward. The event horizon is the place where escape velocity reaches the speed of light, and from that simple fact, an extraordinary conclusion follows. There exists a region of the universe where the future itself points only one way. Light cones at the horizon. To truly understand what the event horizon is, we have to move beyond the simple idea of escape velocity and look at how space and time themselves are arranged near a black hole. Because in Einstein's theory of gravity, objects do not simply move through space while time ticks in the background, but instead space and time form a single fabric called space-time. And everything that exists moves through this fabric along paths that are limited by one fundamental rule, which is that nothing can travel faster than light. Physicists use a simple but powerful tool to describe these limits, and it is called a light cone, which is not a physical object, but a way of drawing all the possible directions that light can travel from a single event in space-time. If you imagine a flash of light going off at one point, the light spreads outward in every direction at the same speed. And if we include time as an upward direction in our diagram, the spreading light forms a cone shape that shows the boundary between what can be influenced by that event and what cannot. Everything inside that cone represents possible future paths that an object moving slower than light can take, and everything outside the cone represents paths that would require faster than light motion and are therefore impossible, which means the light cone defines the limits of cause and effect, because it shows which events can influence others and which cannot. Far away from a black hole, light cones behave normally, meaning they stand upright in space-time diagrams, and the future direction points forward in time, while allowing freedom to move in different spatial directions, so you can travel left or right, or outward or inward, as long as you remain within the light speed limit. And the structure of space-time allows many possible futures. However, as you move closer to a black hole, gravity becomes stronger, and the curvature of space-time becomes more extreme. And this curvature does not just pull objects inward like a simple force, but actually tilts the light cones themselves toward the center of the black hole, which means that the allowed future paths begin to lean inward as well. reducing the range of possible outward motion. At great distances, this tilt is tiny and barely noticeable, but as you approach the event horizon, the tilt becomes dramatic, and the light cones lean so far inward that the outward direction becomes narrower and narrower until, at the exact location of the event horizon, something remarkable happens. Because at that boundary, the light cone tips precisely enough that the edge of the cone, which represents the path of light itself, lies along the horizon, meaning that even a beam of light aimed directly outward cannot move away from the black hole, but instead remains trapped at the boundary. This is the key moment, because if the path of light itself is no longer pointing outward into open space, but instead is directed inward or along the horizon, then every possible future path available to any object, since all objects must move slower than light and therefore remain inside the light cone, is also directed inward, which means that once you cross the event horizon, there is literally no direction in space-time that leads back out. It is important to understand that this boundary is not made of matter and does not behave like a wall or surface that you could collide with, because if you were falling toward a black hole, you would not feel a sudden impact when crossing the event horizon, provided the black hole is large enough to avoid extreme tidal forces at that location. And locally, the laws of physics would appear normal as you pass through. Yet globally, your future would be sealed, because every possible path you could take would lead deeper into the black hole. This is why physicists say that the event horizon is a boundary of causality rather than a material boundary, because it marks the limit beyond which events can no longer influence distant observers. And once something passes inside, no signal it emits can ever reach the outside universe, not because something blocks the signal, but because the structure of a space-time itself no longer contains a path that leads outward to infinity. The tipping of light cones makes this idea precise and visual, since outside the horizon there are still paths that angle away from the black hole and allow escape, while inside the horizon all light cones are tilted so completely inward that even the most powerful engine or the most energetic particle cannot change its fate, as the geometry of space-time dictates that the future lies only toward the center. What makes this even more profound is that the event horizon is defined not by what happens at a single moment, but by the overall shape of space-time extending into the infinite future, because whether a light ray can escape depends on the entire future history of the universe, which means the horizon is a global feature of space-time rather than a local surface with measurable thickness, and its existence depends on the ultimate paths that light can or cannot take. Coordinate versus physical singularity. When the Schwarzschild solution to Einstein's field equations was first published in 1916, it presented a strange feature that puzzled physicists for decades: a point at the Schwarzschild radius where the equations appeared to blow up, with certain terms becoming infinite and the math seemingly breaking down. This was called a singularity, and it caused intense confusion because infinities in physics are often treated as signs that a theory has failed or reached its limits. Many early researchers assumed that this singularity must represent a physical barrier in space, an actual place where the laws of nature fail, a point of infinite density that could not exist in reality. However, the mathematics was more subtle than that. The apparent singularity at the Schwarzschild radius is not an intrinsic property of space-time itself, but arises because of the way the coordinates were chosen to describe the geometry. In Schwarzschild coordinates, which measure distances and times in a particular way, certain components of the metric tensor diverge at the horizon. This divergence makes it appear as if something catastrophic is happening at that radius, even though no physical quantity such as curvature or tidal force necessarily becomes infinite there. Physicists learned that this kind of singularity is a coordinate singularity, not a physical one. A coordinate singularity is an artifact of the system of measurement rather than a real event in space-time, much like how the geographic coordinates of longitude are undefined at the North Pole, even though the physical point exists perfectly well. The problem is not that space-time ceases to exist, or that physics breaks down at the Schwarzschild radius, but that the particular coordinates used to describe it become degenerate and misleading. In other words, the equations make it look as if a boundary or infinity exists, when in reality, the space-time is smooth and continuous. The true nature of the horizon cannot be fully appreciated in the original Schwarzschild coordinates, because those coordinates treat time and radial distance in a way that becomes pathological at the critical radius. To resolve this, physicists developed new coordinate systems that are well behaved at the Schwarzschild radius. Among the most important are the Kruskal-Sekeres coordinates, which completely remove the apparent divergence at the event horizon. In these coordinates, the Schwarzschild radius becomes just another point in space-time with no singular behavior in the geometry. The metric is smooth, finite, and well-defined across the horizon, and the curvature invariants, which are quantities that measure the intrinsic bending of space-time, remain finite at the boundary. By adopting Kruskal-Sekeres coordinates, one can see clearly that the event horizon is not a point of infinite density or infinite tidal forces. It is a regular region of space-time, where the paths of light and matter become constrained in a fundamental way. The distinction between coordinate and physical singularities is critical because it explains why an observer falling into a black hole experiences nothing unusual when crossing the event horizon, assuming the black hole is sufficiently large. A small black hole with a mass a few times that of the Sun produces enormous tidal forces near the horizon, stretching and compressing any infalling object. But for supermassive black holes millions or billions of times the Sun's mass, the curvature at the horizon is mild and essentially undetectable locally. The person or object crossing the horizon would notice no sudden change, no wall, no flash of infinite energy, nothing dramatic at all. Locally, physics behaves as normal. The horizon is invisible and non-physical in the local sense. It only becomes meaningful when one considers the global geometry and the causal structure of space-time. This understanding is what finally allowed physicists to reconcile the seemingly paradoxical features of black holes. How an infalling observer can pass smoothly across the horizon, while a distant observer never sees them cross it. In Schwarzschild coordinates, the distant observer's clock measures signals from the infalling object as increasingly redshifted and delayed, approaching infinity as the object nears the horizon. This is a real relativistic effect called gravitational time dilation, which arises because clocks deeper in a gravitational well run slower relative to distant clocks. However, the divergence seen in Schwarzschild coordinates at the horizon is partly due to the coordinate system itself. By switching to Kruskal-Sekeres coordinates, the singular behavior disappears, and one sees that the crossing occurs in finite proper time for the infalling observer. The apparent freezing of motion at the horizon for distant observers is a combination of physical time dilation and coordinate representation, not a sign of a physical barrier. The development of these more sophisticated coordinate systems marked a turning point in the study of black holes because it clarified what the horizon actually is. It is not a wall or a surface in the conventional sense. It is not made of matter, and it does not produce an infinite force at the boundary. It is a globally defined surface in space-time, a causal boundary that separates regions that can communicate with infinity from regions that cannot. Its defining feature is that all future directed paths inside the horizon are directed inward, leading inevitably toward the singularity at the center. Yet locally, space-time remains smooth, continuous, and well-behaved. Understanding this distinction allowed physicists to move past decades of confusion about whether black holes were physically real or just mathematical artifacts. The Kruskal-Sekeres coordinates also revealed something surprising and profound. The event horizon is a perfectly smooth, null surface, meaning it is made up of light-like paths that define the boundary between escape and inescapability. It is neither static nor a fixed shell. Rather, it is defined by the geometry of spacetime itself and the light cones that tip inward at the boundary. This null surface is what enforces the causal disconnection between the interior of a black hole and the external universe. It shows that the horizon is not the singularity at the center, which is a point where curvature invariants diverge and general relativity itself may break down, but rather the surface that dictates what can and cannot influence the outside world. The singularity at the center remains hidden behind this smooth horizon, safely enclosed within the causal boundary. Another critical insight from this work is that the event horizon is a global property of spacetime. Its existence cannot be determined by local measurements alone. An observer cannot tell they are at the horizon simply by looking around or measuring curvature in their immediate vicinity. The horizon's location is determined by tracing the possible paths of light into the infinite future. If a light ray sent outward eventually fails to escape to infinity, the starting point of that ray lies inside the event horizon. This global perspective makes black holes fundamentally different from ordinary objects. They are defined by the geometry of the universe as a whole, not by any local material surface or physical boundary. The realization that the Schwarzschild singularity is merely a coordinate artifact also paved the way for the exploration of rotating and charged black holes, where the horizons are even more complex. In the Kerr and Kerr-Newman solutions, the horizons take on shapes and behaviors that are entirely smooth locally, but the global causal structure becomes richer, with ergospheres and inner horizons appearing in addition to the outer event horizon. In all cases, the key insight remains the same. The horizon is not a place of violent disruption, but a boundary in spacetime that organizes the future trajectories of matter and light. By the 1960s, physicists fully understood that the coordinate singularity in Schwarzschild coordinates was an illusion, and that the true horizon is smooth, locally unremarkable, and globally defining. This clarity resolved long-standing debates about the nature of black holes and allowed researchers to focus on real questions about their formation, behavior, and observable effects. It also made it possible to predict phenomena such as gravitational time dilation near the horizon, the appearance of infalling matter to distant observers, and the role of the horizon in shaping the emission of radiation and gravitational waves. The transition from confusion about coordinate singularities to the recognition of smooth horizons was more than a technical detail. It reshaped our understanding of what it means to fall into a black hole and what it means to observe one from a distance. It revealed that the universe contains regions from which information cannot escape, not because of a physical wall, but because the geometry of spacetime itself bends all paths inward. The Kruskal-Sekeres coordinates, along with other advanced mathematical tools, allowed physicists to visualize these boundaries clearly, separating the illusions caused by poorly chosen coordinates from the real, physically meaningful structures that govern the behavior of light, matter, and causality near black holes. This insight also set the stage for future breakthroughs in black hole physics, including the study of Hawking radiation, black hole thermodynamics, and the deeper connections between gravity, quantum mechanics, and information theory. By distinguishing between coordinate artifacts and true physical features, physicists could confidently explore the consequences of event horizons without being misled by the misleading infinities in older coordinate systems, laying the foundation for a century of discoveries that would transform our understanding of the cosmos. The event horizon is therefore a perfectly smooth, continuous surface in spacetime, entirely defined by geometry and causality, completely free of the pathology suggested by the original Schwarzschild coordinates, and it provides a lens through which the structure of the universe, the flow of time, and the ultimate fate of matter and information can be understood. It is the boundary that separates what can influence the outside universe from what cannot, the tipping point at which all possible future paths are redirected inward, and the feature that makes black holes, despite being invisible and locally unremarkable, one of the most dramatic and fascinating predictions of Einstein's theory of general relativity. Proper time versus distant observer time. Once we understand that the event horizon is a smooth, global boundary in spacetime and not a physical wall, the next step is to grasp how time itself behaves differently for observers near a black hole versus those far away. Because general relativity teaches us that time is not universal. It flows at different rates depending on the curvature of spacetime caused by gravity. And the closer you are to a massive object, the slower time passes relative to someone far away. To see this in action, imagine an astronaut falling toward a black hole while a distant observer watches from a safe distance far away, where spacetime is nearly flat. From the astronaut's perspective, nothing extraordinary happens when crossing the event horizon if the black hole is sufficiently large. The astronaut experiences a continuous progression of events and reaches the horizon in finite proper time, meaning the time measured by their own clock. For them, the journey is smooth and uninterrupted, and the laws of physics behave normally. Their rocket still fires, their instruments still function, and they cross the boundary without noticing anything unusual, entirely unaware that they have passed a point beyond which no signal can ever return. Meanwhile, for the distant observer, the story appears completely different. As the astronaut approaches the event horizon, their signals, light, radio transmissions, or any other form of information, become increasingly redshifted and delayed. The closer they get, the slower their clock appears to tick from the distant viewpoint. If we track the signals mathematically, using the Schwarzschild metric, the relationship between the proper time of the falling observer and the coordinate time of the distant observer is given by the gravitational time dilation formula. T prime equals t square root of 1 minus 2, joule m over rc squared. Where is the proper time experienced by the falling observer? Is the time measured by the distant observer? Is the gravitational constant? Is the mass of the black hole? Is the radial coordinate of the observer? And is the speed of light? As the radial coordinate approaches the Schwarzschild radius, the factor under the square root approaches 0. Meaning that from the distant observer's perspective, the falling clock slows toward a standstill, and the astronaut appears to freeze at the horizon, never quite crossing it. The light they emit becomes infinitely redshifted, fading into darkness, as if time itself refuses to allow them to move beyond the boundary. This striking contrast is not a paradox, but a direct consequence of the curvature of spacetime near a black hole. Proper time, which is the time measured locally along an object's world line, continues normally for the falling observer because locally spacetime is smooth and the horizon produces no singular effects. Coordinate time, or the time measured from a distant, essentially flat region of spacetime, stretches to infinity at the horizon because of the extreme warping of the temporal dimension. In effect, the horizon acts like a lens on time. Near it, events for a distant observer appear to slow down and asymptotically freeze, while locally they proceed without interruption. This difference between proper time and distant observer time also explains why black holes appear so mysterious and paradoxical to the outside universe. While an infalling astronaut crosses the horizon in minutes or hours, a distant observer never actually sees the crossing happen. All they see is the astronaut approaching more and more slowly, fading and reddening, eventually disappearing from view. This is why black holes can appear to trap light without requiring any sudden or violent barrier. The event horizon ensures that signals emitted inside cannot escape, while signals from just outside experience extreme gravitational time dilation. Moreover, this effect is not limited to astronauts or spaceships. Matter falling into a black hole, gas, dust, or even whole stars appears to slow down and spread out near the horizon from a distant viewpoint, creating the illusion of a glowing frozen shell just outside the black hole. In reality, the matter passes through the horizon smoothly and continues inward, but our observations are constrained by the limits imposed by the curvature of space-time and the speed of light. The event horizon thus separates what can communicate with the rest of the universe from what cannot, defining a boundary not in material terms, but in terms of cause and effect across time. The profound implications of proper time versus distant observer time extend to the study of gravitational waves, black hole mergers, and astrophysical processes. When two black holes spiral toward each other and merge, the extreme warping of time and space around their horizons shapes the signals detected by observers far away, stretching, compressing, and modulating the gravitational waves in ways that reveal the dynamics near the horizons, yet never allow direct observation of matter crossing them. In all cases, the distinction between local proper time and distant coordinate time is essential for understanding how information travels and how the black hole interacts with its environment. Understanding this difference also highlights why the event horizon is such a unique feature of black holes. It is not a physical surface or a boundary that produces a sudden effect locally. It is a global property of space-time that organizes the flow of time itself. For an infalling observer, it is entirely ordinary, while for a distant observer, it represents the ultimate temporal limit, where clocks slow to a crawl and the future of anything inside becomes inaccessible. It demonstrates how gravity and the curvature of space-time reshape our fundamental notions of time, causality, and observation, creating regions where the universe can watch without ever being able to reach, and where events proceed normally but are forever hidden from the outside world. The horizon enforces a dual perspective on time, one governed by the local experience of the infalling observer, which continues smoothly and naturally, and one governed by the distant observer, which stretches and distorts indefinitely, creating the iconic image of objects appearing to freeze at the edge of a black hole. This duality is a direct consequence of general relativity, and it provides the foundation for our understanding of black holes as objects defined by the structure of spacetime and the limits of causal influence, rather than by any tangible, physical boundary that could be touched or seen in the conventional sense. The proper time of the infalling object and the coordinate time of the distant observer together reveal the full picture of the event horizon, showing both the local continuity of physics and the global consequences of space-time curvature, and explaining why black holes are simultaneously invisible, inescapable, and yet entirely natural in the framework of relativistic physics. The freeze effect, gravitational redshift. Imagine standing on a distant hill, looking at a star sinking slowly toward a black hole. At first, it shines brightly, a familiar point of light against the dark sky, but as it moves closer to the event horizon, something strange happens. Its color begins to shift, stretching from familiar hues toward deeper red, the light itself fading in intensity until it becomes almost impossible to see. This is not an illusion caused by dust or distance, but a direct consequence of gravitational redshift, a phenomenon predicted by Einstein's theory of general relativity, which tells us that light traveling out of a strong gravitational field loses energy. Light is an electromagnetic wave oscillating at a certain frequency, and the energy of each photon is proportional to that frequency. When a photon climbs out of the deep gravitational well of a black hole, it must expend energy to escape, but since it cannot slow down or stop, the only way its energy can decrease is for its frequency to lower. As the star approaches the horizon, the escape velocity for any signal increases, approaching the speed of light, and the stretching of the spacetime itself causes the frequency of the light leaving the star to drop towards zero. The visible light that reaches a distant observer is progressively shifted toward the red end of the spectrum, eventually stretching into infrared, microwave, and then radio waves, fading from view completely. From a distant perspective, the star appears to slow down, moving more and more slowly as it approaches the event horizon. Each successive photon takes longer to climb out of the gravitational well, and the light emitted later appears dimmer and redder than the light emitted earlier. The star does not disappear because it suddenly ceases to exist, but because the gravitational redshift stretches its light so much that it is effectively invisible. Its image seems frozen at the edge of the horizon, a haunting silhouette that never quite crosses the boundary in the distant observer's frame. This effect is entirely natural in relativity and requires no exotic forces or barriers. The event horizon itself is not a wall, and the object continues its inward journey unhindered in its own proper frame. But the light it emits is dragged into longer and longer wavelengths as it struggles against the deep curvature of spacetime, producing the iconic visual of objects frozen at the brink of a black hole. The combination of stretching light and fading intensity gives rise to what astronomers describe as the freeze effect, a vivid demonstration of how gravity warps not only space, but time, and the very signals that convey information to the outside universe. Because light cannot outrun the curvature of spacetime near the horizon, the frequency of photons reaching a distant observer approaches zero, and the object becomes infinitely redshifted. In this way, the event horizon hides what is inside without creating a physical blockade. It is the geometry of spacetime itself, coupled with the finite speed of light, that produces this remarkable visual freezing, blending physics and perception into one of the most striking predictions of general relativity. The freeze effect, information delay. While gravitational redshift explains why an object falling toward a black hole appears to fade and redden to a distant observer, the story becomes even more intriguing when we consider how the information carried by light and other signals behaves near the event horizon. Signals emitted by the infalling object take progressively longer to reach a distant observer because the curvature of space-time stretches their paths and slows the rate at which successive photons can climb out of the gravitational well. Unlike in flat space, where light travels in straight lines at a constant speed, the extreme warping of space-time near a black hole forces photons to travel along curved paths that are increasingly tilted toward the center. As a result, each photon must traverse a more intense gradient of gravitational potential, which stretches the time intervals between the arrivals of successive signals, making it appear as though the object is slowing down and freezing at the horizon. This phenomenon can be understood mathematically using the Schwarzschild metric, which describes the geometry outside a spherically symmetric, non-rotating black hole. If a signal is emitted from a radial coordinate close to the Schwarzschild radius, the coordinate time measured by a distant observer to receive that signal diverges according to the equation t equals integral of dr over c times the square root of 1 minus r sub s over r, where c is the speed of light. As approaches infinity, the denominator approaches zero, causing the coordinate time to approach infinity. In physical terms, the last photon emitted before crossing the horizon requires an infinite amount of coordinate time to reach the distant observer. This is why, from the faraway viewpoint, the infalling object seems to freeze indefinitely at the edge of the event horizon. No matter how long one waits, the distant observer never sees the object actually pass through the horizon, although they can still see the light that was emitted earlier, stretched into longer wavelengths by gravitational redshift. It is crucial to emphasize that this does not imply the infalling object never crosses the horizon. In its own proper time, which is the time measured along its own trajectory, the crossing occurs in a finite duration, with nothing particularly special experienced at the horizon itself. The distinction arises because coordinate time and proper time are not the same in a strongly curved gravitational field. Proper time follows the world line of the object, measuring events from its own perspective, while coordinate time represents the time of a distant observer for whom spacetime is approximately flat. The divergence of coordinate time near the horizon is a reflection of the extreme warping of spacetime and the resulting causal structure, not a signal that the physical process is suspended or halted. This difference in frames of reference is a fundamental feature of relativity. Einstein's equations dictate that time is not absolute. It depends on the path taken through spacetime. Near a black hole, this effect becomes extreme, producing phenomena that seem paradoxical only when we try to interpret them from a single classical perspective. The freeze effect, with its infinite delay in signals from the infalling object, is a striking illustration of how relative motion and gravitational fields intertwine to shape our perception of events. It demonstrates that the universe allows for radically different experiences of time depending on location and gravitational environment, without violating any physical laws or creating contradictions. The implications for information transfer are profound. Since the last photon takes infinite coordinate time to reach a distant observer, it is effectively impossible for any observer outside the horizon to receive complete information about events that occur inside. This leads to the concept of causal disconnection. The event horizon separates spacetime into regions where signals can reach infinity and regions where they cannot. Information emitted from inside the horizon is forever inaccessible to the outside universe. Yet locally, inside the horizon, all processes continue normally. Particles interact, atoms exist, and physics operates as expected. The horizon does not destroy information in a local sense. It merely hides it from external observers. From the perspective of astrophysics, this behavior explains why black holes appear dark and invisible despite the continuous infall of matter. Accreting material emits radiation as it spirals toward the horizon, creating bright disks that shine across multiple wavelengths. However, once the material crosses the horizon, no signal can escape, and any photons emitted from within this boundary are redshifted into oblivion. The freeze effect ensures that the horizon itself is a one-way boundary. Light and matter can enter, but cannot exit. This provides a consistent explanation for both the visual disappearance of infalling matter and the maintenance of local physical laws inside the black hole. The freeze effect also influences the way we observe time-dependent phenomena near black holes. Consider an X-ray binary system in which a stellar mass black hole accretes material from a companion star. Material spiraling inward emits X-rays that vary with its density, speed, and temperature. To a distant observer, the signals from material approaching the horizon appear increasingly stretched and delayed, altering the timing and shape of the observed light curves. The freeze effect must be accounted for in interpreting these observations, because what is observed is a combination of local emission processes and the extreme time dilation imposed by the black hole's gravity. Without understanding this effect, one might misinterpret the timing or dynamics of accretion processes. Another fascinating consequence arises in the context of gravitational waves. When black holes merge, the extreme warping of spacetime near their horizons shapes the gravitational waveforms detected by instruments like LIGO and Virgo. The delay in signals from near horizon regions affects the amplitude and phase of the waves as they propagate to distant detectors, providing indirect evidence of the freeze effect in action. In this way, gravitational waves allow us to hear the structure of spacetime around event horizons, complementing electromagnetic observations and giving us a more complete understanding of how the freeze effect governs information transfer. The freeze effect also raises deep questions about the nature of reality and observation. To the distant observer, the infalling object seems frozen at the horizon, never completing its journey. Yet in the object's own frame, it crosses the horizon in finite time and continues toward the singularity at the center. Both perspectives are correct within their respective frames, illustrating the profound relativity of simultaneity and measurement in curved spacetime. There is no contradiction because the laws of physics are local and consistent along each observer's world line. The apparent paradox exists only if one tries to impose a single, global notion of time across regions where spacetime is strongly curved. The freeze effect also underlines the subtlety of causal structure in general relativity. Events inside the horizon cannot influence the outside universe, but the horizon itself, defined by the last light rays that can escape, is a perfectly smooth surface in spacetime. It is not a barrier in the conventional sense, but a limit imposed by geometry. Signals emitted arbitrarily close to the horizon experience extreme redshift and delay, creating the illusion of freezing, while still adhering to the fundamental speed limit set by light. In this way, the freeze effect is both a visual phenomenon and a deep statement about the structure of spacetime. It encodes the causal disconnection between the interior and exterior of a black hole, without violating any local laws of physics. From a conceptual standpoint, the freeze effect shows that events inside a black hole are effectively hidden from the outside world, while remaining fully ordinary locally. The infinite delay in signals is not a failure of physics, but a natural consequence of the warping of time near an extreme gravitational field. Observers far away are forced to interpret a world in which time slows dramatically as objects approach the horizon. Yet this slowing is frame-dependent and does not constrain the proper experience of the infalling object. In relativity, such frame-dependent effects are not paradoxical but essential features of the theory, demonstrating the richness and flexibility of spacetime in extreme conditions. The freeze effect also ties directly into the concept of black hole thermodynamics and information theory. Since the horizon effectively prevents information from escaping, it establishes a natural boundary for defining entropy and energy flows in the system. The apparent freezing of matter and radiation near the horizon allows physicists to assign thermodynamic properties to the black hole as a whole, leading to the formulation of concepts such as the Bekenstein-Hawking entropy, Hawking radiation, and the ultimate fate of information in black hole evaporation. The delay in information transfer is central to these ideas because it separates local dynamics inside the horizon from what can influence the exterior universe, providing the foundation for modern theoretical explorations of quantum gravity and black hole information paradoxes. In the end, the freeze effect is both a visual and conceptual window into the strange nature of black holes. It explains why infalling objects appear frozen and reddened at the horizon, why signals from near the horizon are delayed infinitely, and why no contradiction arises between the infalling observer's proper experience and the distant observer's perception. It highlights the frame-dependent nature of time in general relativity, the global structure of event horizons, and the limits imposed on information transfer by the curvature of spacetime. By examining how light and signals behave near a black hole, we gain a deeper understanding of why these objects are not just invisible, but fundamentally inaccessible from the outside, illustrating the profound interplay between gravity, causality, and observation in one of the most extreme environments in the universe. The freeze effect, therefore, is far more than a curious visual trick. It is the direct consequence of space-time geometry and the universal speed limit shaping our perception of time, motion, and information near a black hole, while remaining fully consistent with relativity, proper time, and the local laws of physics. It is the phenomenon that makes event horizons simultaneously smooth, invisible, and causally defining, capturing the essence of what it means for a black hole to hide part of the universe from view while remaining entirely ordinary to those who dare to cross its threshold. Radial direction becomes time-like. Crossing the event horizon of a black hole is unlike anything experienced in everyday life or even in most extreme environments in the universe, because once you pass this boundary, the nature of space and time itself changes in a way that is deeply counterintuitive, yet entirely dictated by the geometry of space-time as described by general relativity. Outside the horizon, the radial coordinate behaves as a normal spatial dimension. You can move inward or outward freely, choosing your path in the radial direction just as you can choose to walk north or south. However, the moment you cross the event horizon, this relationship flips, and the radial coordinate takes on a time-like character. In other words, moving inward toward the singularity becomes as unavoidable and directional as moving forward through time. It is no longer a choice, but a fundamental requirement imposed by the structure of space-time itself. To understand this, we need to revisit the concept of a light cone, which represents all the possible directions that light, and therefore any object moving slower than light, can travel from a given event in space-time. Outside the horizon, light cones are tipped slightly toward the black hole, reflecting the pull of gravity, but there remain directions that allow escape and movement away from the center. Inside the horizon, the curvature of space-time is so extreme that the light cones tip completely inward. The future-directed paths, which define what any particle can do moving forward in time, are all oriented towards smaller, meaning that every possible trajectory inexorably leads toward the center of the black hole. No matter how fast you move, how you orient your momentum, or what propulsion you use, there is literally no direction that leads outward. You are compelled to move inward as naturally and unavoidably as you move forward through seconds in your own proper time. This flipping of the radial coordinate from space-like to time-like is not just a mathematical quirk, it has profound physical consequences. Inside the horizon, the concept of hovering or moving outward becomes impossible. If you attempt to remain at a fixed radial coordinate inside the horizon, the laws of physics make it unattainable. Doing so would require exceeding the speed of light, which is forbidden by relativity. Your forward progression toward the singularity is as inevitable as the passage of time itself, which means that from the moment of crossing, your trajectory is predetermined by the geometry of space-time. While outside observers may never see you cross the horizon due to extreme gravitational time dilation and the freeze effect, your own experience is continuous and smooth, yet every moment brings you closer to the ultimate center of the black hole. This redefinition of space and time challenges our intuitive notions of motion and causality. In normal experience, space and time are distinct, and motion is a choice that we can reverse or redirect. Inside the horizon, the laws of general relativity dictate that one spatial dimension becomes as rigid and directional as time, erasing the freedom to resist the pull of the singularity. The interior of a black hole is therefore a region where geometry itself determines the inevitable, converting what was once a spatial option into a temporal necessity, and making the inward fall unavoidable, even if locally nothing seems to act upon you in a conventional sense. Understanding this radical transformation is essential for visualizing what happens inside a black hole. The event horizon is not a barrier or a wall, but a threshold beyond which the ordinary distinction between space and time ceases to hold in familiar ways. Radial motion becomes tied to the arrow of time, and all events, all motions, and all trajectories are constrained to follow this inexorable inward path. This is why physicists describe the singularity as lying in your inevitable future, rather than simply at a location in space. Crossing the horizon means your destiny is no longer a matter of choice. It is encoded in the very fabric of space-time. This shift also clarifies why discussions of escape velocity or centrifugal forces become meaningless inside the horizon. The traditional notion of speed needed to escape loses all applicability because the geometry has turned the radial coordinate into a one-way street, and no force or acceleration can redirect you outward. Everything inside the horizon moves forward in time towards smaller, and your proper time continues normally as you fall. This insight reconciles the apparently paradoxical ideas that the horizon is smooth locally, that an object can cross without noticing, and yet no signal can ever return. The laws of physics inside the horizon are fully regular, but they dictate a trajectory from which there is no turning back. The inevitability of inward motion also provides a deeper understanding of causality within a black hole. Events that occur inside the horizon can influence other events deeper inside, but none of these can affect the outside universe. The interior is causally sealed. The future-directed paths all terminate at the singularity, making the singularity not merely a location, but the ultimate temporal endpoint for anything that crosses the horizon. In this sense, the horizon acts as a demarcation line in space-time itself, separating regions where motion and causality can affect infinity from regions where the laws of physics force all matter and information inward along predetermined paths. In practical terms, imagining life inside the horizon requires abandoning the usual notion of radial freedom. All effort, all motion, all choices in that dimension are equivalent to moving forward through time, unavoidable and irreversible. This gives a powerful visual for understanding why black holes are fundamentally different from any other object in the universe. They are not extreme in terms of density at the horizon or in terms of material interaction, but in terms of the structure of space-time itself. Here, space has been converted into a temporal directive, and the journey toward the singularity is as real and continuous as the passage of time experienced by any observer. Physically, this means that phenomena like rockets or jets cannot counter the inward motion. Even if an astronaut fires thrusters at maximum capacity, the direction they can push in is constrained to their forward world line. Outward, in the radial sense, is no longer accessible, because radial motion is now locked to the arrow of time. From the falling observer's perspective, they continue experiencing seconds, minutes, or hours as usual. But the entire geometry of space-time ensures that each moment brings them closer to the center. In this sense, crossing the event horizon is like stepping onto a conveyor belt moving inexorably forward, locally smooth and imperceptible, globally inescapable and absolute. The transformation of the radial coordinate into a time-like direction also underscores why the event horizon has such a profound effect on information and observation. No matter what signals or light the infalling object emits, those signals cannot move outward once inside the horizon, because the allowed directions of motion are all aligned inward. Light and information are trapped by the geometry itself, rather than by any material obstruction. This gives the horizon its defining causal character. It separates what can communicate with the outside universe from what cannot, enforcing a strict boundary in the temporal and spatial structure of the black hole's interior. From a theoretical standpoint, this insight has driven decades of research into black hole interiors, singularities, and the ultimate fate of matter. Understanding that radial motion becomes time-like frames the problem of the singularity not as a spatial location to avoid, but as a future event that all trajectories inevitably reach. It also informs modern explorations into quantum gravity, where researchers attempt to reconcile the smooth space-time of general relativity with quantum uncertainty and the behavior of information at the horizon. The inevitability of inward motion underpins thought experiments and models, from the classic depiction of infalling observers to the more recent proposals about firewalls, complementarity, and horizon information storage. Tidal forces. Once we fully grasp that inside the event horizon the radial coordinate behaves like time, and that moving inward is as inevitable as moving forward in time, the next layer of reality reveals itself through the effects of tidal forces and the singularity at the center, which represent the true physical extremes of a black hole, rather than the smooth horizon itself. While the horizon is a perfectly regular, non-physical boundary, the singularity is where space-time curvature becomes infinite in the classical sense, and the forces acting on objects reach extremes that stretch the imagination, giving rise to phenomena such as spaghettification. Tidal forces arise because gravity is not uniform across an extended object. A human falling feet first into a stellar mass black hole, for instance, experiences a gradient in gravitational acceleration. The feet closer to the singularity are pulled more strongly than the head. As the object approaches smaller radial coordinates, this differential increases rapidly. Outside the horizon, these tidal forces may already be significant near the surface of the black hole, but the effect becomes extreme inside for typical stellar mass black holes, stretching the body lengthwise and compressing it horizontally into a long, thin shape, reminiscent of spaghetti, a process that gives spaghettification its evocative name. The strength of these tidal forces is determined by the mass of the black hole and the distance to the singularity. Smaller black holes produce far stronger forces near the horizon, while supermassive black holes, millions or billions of times the mass of the Sun, have horizons so large that tidal forces at the event horizon are weak and nearly imperceptible to an infalling observer. This counterintuitive fact arises because the curvature of space-time at the horizon scales inversely with the square of the black hole mass, meaning that while a stellar mass black hole violently stretches matter at the horizon, a supermassive black hole allows an observer to pass the horizon with negligible tidal effects, experiencing only the inevitability of inward motion. Beyond tidal forces lies the singularity, which is the ultimate fate of any matter or observer that crosses the event horizon. The singularity is located at the center of the black hole and represents a point where the curvature of space-time becomes infinite and classical, general relativity breaks down. Unlike the horizon, which is smooth and locally unremarkable, the singularity marks the breakdown of our current understanding of physics. No known physical law can describe what happens to matter or information at this point, and tidal forces diverge to infinity, compressing and stretching any object to a state beyond recognition. For a stellar mass black hole, this occurs quickly after crossing the horizon, whereas for a supermassive black hole, the singularity lies far deeper in the gravitational well, allowing for a comparatively long journey inside the horizon before encountering these ultimate extremes. It is important to emphasize that the singularity is not the event horizon. It is hidden behind the horizon and causally disconnected from the external universe. The horizon itself imposes a one-way boundary. Everything inside moves inevitably toward the singularity, but nothing at the horizon directly indicates the violent physics that will occur at the center. From a distant observer's perspective, all processes inside are frozen at the horizon due to gravitational time dilation and the freeze effect, and no information about the singularity itself ever escapes to reveal the extreme tidal forces or the breakdown of space-time that lie within. This separation between horizon and singularity has profound consequences for how we understand black holes in astrophysics and theoretical physics. Observationally, all that can be detected are the effects of matter outside the horizon, such as accretion disks, relativistic jets, and gravitational waves produced during mergers. The actual interior, including tidal forces and the singularity, remains inaccessible, shielded by the causal structure of spacetime. Yet theoretical models allow us to predict the behavior of infalling matter and the ultimate fate of objects that pass the horizon, providing insight into the extremes of physics that cannot be replicated anywhere else in the universe. The distinction between stellar mass and supermassive black holes also highlights the variability of tidal effects at the horizon. While a human falling into a typical stellar mass black hole would be spaghettified almost immediately, an astronaut entering a supermassive black hole could cross the horizon entirely intact, only to encounter destructive tidal forces much later, possibly near the singularity itself. This demonstrates that the experience of falling into a black hole is highly dependent on its mass, and that the event horizon is not inherently a violent region. The violence lies deeper in the curvature of spacetime that eventually overwhelms any material object. In addition, tidal forces inside the horizon affect not only matter, but also the propagation of light and other signals. The extreme curvature ensures that all trajectories, whether of particles or photons, are redirected inward, concentrating the motion toward the singularity. This geometric funneling amplifies the stretching and compressing effects on matter and radiation, enhancing the physical consequences of falling deeper into the black hole. The horizon itself does not contribute to these forces. It merely marks the boundary beyond which no path leads outward, after which tidal forces become the dominant physical effect. From a theoretical standpoint, understanding tidal forces and singularities inside the horizon has driven research into quantum gravity, the limits of general relativity, and the information paradox. The classical description predicts inevitable destruction of matter at the singularity, yet quantum theory suggests possibilities for new physics, such as the preservation of information or the existence of non-singular cause. These investigations rely on the clear separation between the smooth, causally defining event horizon and the violent, physically extreme singularity, emphasizing the layered structure of black holes and the complex interplay between geometry, causality, and physical forces. Ultimately, the interior of a black hole is a realm where ordinary intuition fails. The event horizon introduces the inevitability of inward motion. Tidal forces impose extreme physical constraints, and the singularity represents the breakdown of known physics. Together, these features reveal why black holes are the most extreme objects in the universe. They combine smooth, invisible boundaries with hidden, destructive interiors, all governed by the geometric laws of space-time rather than by conventional material interactions. Understanding these layers provides a coherent picture of what happens once matter crosses the horizon, and highlights the profound difference between the calm inevitability of crossing the horizon and the violent extremes encountered deeper within. In this way, the event horizon is a gateway to a universe where radial motion becomes time, where tidal forces can stretch and compress matter to unimaginable degrees, and where the singularity stands as the ultimate endpoint, the place where our current understanding of space-time ceases to apply. It is inside this boundary that general relativity reaches its limits, and where the true mysteries of black hole interiors challenge our understanding of physics, geometry, and the flow of time itself, revealing the astonishing structure and hidden drama that lie at the heart of these enigmatic cosmic objects. The Kerr solution, 1963. In 1963, Roy Kerr, a mathematician from New Zealand, uncovered one of the most astonishing solutions to Einstein's equations, revealing a completely new class of black holes, those that rotate. Until Kerr's discovery, black holes were imagined as static, spherically symmetric objects described by the Schwarzschild solution, with a single event horizon and a singularity at the center. Kerr's solution changed that picture entirely, showing that black holes could spin, and that this rotation would fundamentally alter the structure of space-time around them, creating effects that were impossible in a non-rotating black hole. A Kerr black hole is characterized not only by its mass, but also by its angular momentum. Its rotation drags space-time along with it, twisting the geometry in a phenomenon known as frame dragging. Unlike a Schwarzschild black hole, where the horizon is simply a spherical boundary, a Kerr black hole introduces a more complex geometry. The event horizon becomes oblate due to rotation, flattened at the poles and bulging at the equator, while the singularity itself transforms from a point into a ring, spinning at incredible speeds and introducing fundamentally new possibilities for physics near the black hole. This solution revealed immediately that rotation could produce surprising features, such as the ergosphere, a region outside the event horizon where space-time is dragged so forcefully that nothing can remain stationary relative to distant observers. Kerr's mathematics showed that within this region, all objects are compelled to co-rotate with the black hole, moving along with the twisting space-time, a direct consequence of the way angular momentum influences the geometry of the surrounding universe. The equations also indicated that, unlike a static black hole, a rotating black hole could, in principle, allow for the extraction of energy from its spin, a counterintuitive and revolutionary idea that would later be explored in what is known as the Penrose process. Kerr's solution was more than just a mathematical curiosity. It profoundly changed our understanding of astrophysical black holes. Real black holes are unlikely to be completely static, because any collapsing star that retains even a small amount of angular momentum would naturally spin, and the Kerr metric provided the first realistic framework to describe such objects. It also introduced the possibility of more intricate horizons, with inner and outer boundaries that define regions of causality in surprising ways, and opened the door to questions about stability, accretion, jets, and how matter behaves in the extreme gravitational and rotational environment near a spinning black hole. Ergosphere and two horizons. Building on the revolutionary Kerr solution, the interior and exterior structure of a rotating black hole reveals phenomena far stranger than anything encountered around a non-rotating black hole, starting with the ergosphere, a region outside the event horizon defined by extreme frame dragging and the possibility of energy extraction. Unlike the static Schwarzschild black hole, a Kerr black hole drags space-time around itself, forcing any object within the ergosphere to move in the direction of the black hole's spin. This occurs because the rotation of the black hole twists the fabric of space-time, tilting light cones so severely that all future directed paths are compelled to co-rotate. In this sense, the ergosphere is a realm where standing still relative to distant stars becomes physically impossible. Even photons are swept along the rotation of space-time, moving inevitably in the direction of the spin. The shape of the ergosphere is oblate and varies with latitude. At the poles, it coincides closely with the outer event horizon, but near the equator, it extends significantly outward, creating a bulbous region where space-time is twisted to extremes. It is within this distorted geometry that one of the most remarkable possibilities in astrophysics arises. Energy can be extracted from the black hole. Through the Penrose process, a particle entering the ergosphere can split into two, with one fragment falling into the black hole and the other escaping to infinity with more energy than the original particle. This is not magic, but a direct consequence of how rotation modifies the conservation of energy in curved, rotating space-time. The black hole loses a tiny fraction of its rotational energy in the process, demonstrating that spinning black holes are not just cosmic traps, but potential sources of extractable energy. Rotating black holes also feature not one, but two horizons. The outer event horizon, which functions much like the horizon of a Schwarzschild black hole in marking the boundary of no return, and an inner horizon known as the Cauchy horizon. The outer horizon is oblate due to the spin and defines the point at which all inward motion becomes inevitable. Once crossed, all paths lead inward, just as in the non-rotating case, but with added complexity from angular momentum. The inner horizon represents a further limit within the black hole, separating regions where the determinism of classical general relativity becomes subtle. Beyond the Cauchy horizon, spacetime exhibits potential instabilities and challenges for predictability, raising deep questions about the ultimate fate of matter and information inside a spinning black hole. The combination of the ergosphere and two horizons makes Kerr black holes vastly more complex than their static counterparts. Matter accreting onto a spinning black hole does not simply fall straight inward, but interacts with frame-dragging effects, potentially forming energetic jets along the rotational axis and redistributing energy in ways impossible in non-rotating systems. Photons and particles spiral around, dragged by the rotating spacetime and the innermost stable orbit shift depending on the spin, influencing the structure of accretion disks and the radiation we can observe. The Kerr geometry predicts that the faster a black hole spins, the more pronounced these effects become, with the ergosphere expanding and the inner horizon moving closer to the singularity, modifying the flow of energy and matter in the black hole's vicinity. From an observational standpoint, rotating black holes provide a rich tapestry of signatures for astronomers. The shape and behavior of relativistic jets, the frequency and timing of X-ray emissions from accretion disks, and even gravitational wave signals from merging black holes all carry imprints of the spin, ergosphere, and horizon structure predicted by the Kerr solution. These phenomena allow scientists to infer not only the mass, but also the angular momentum of black holes, confirming that the vast majority of astrophysical black holes are indeed rotating and exhibiting the exotic behaviors Kerr predicted more than half a century ago. Inside the outer horizon, the inner Cauchy horizon introduces a further layer of intrigue. While an infalling observer crosses the outer horizon without experiencing anything unusual locally, approaching the inner horizon may expose them to extreme tidal and radiative effects, potentially magnified by instabilities in the curved spacetime. The precise physics here remains a frontier of theoretical research, but the inner horizon illustrates that rotating black holes are not just more complicated externally, they are more intricate internally, with layers of causal structure and regions where predictability, determinism, and the classical description of spacetime itself are tested. Charged black holes and Hawking radiation. In general relativity, black holes are often introduced in their simplest form, massive, non-rotating and electrically neutral objects that warp spacetime in a perfectly spherical fashion. Yet the equations of Einstein allow for far more exotic possibilities, among them the existence of charged black holes. The Reissner-Nordström solution, discovered independently in the early 20th century, describes a black hole that carries an electric charge in addition to its mass. Unlike the Schwarzschild solution, which has a single event horizon marking the boundary of no return, the Reissner-Nordström metric predicts a more complex structure with multiple horizons, an outer event horizon and an inner Cauchy horizon. The outer horizon functions similarly to the neutral black hole, defining the point beyond which nothing can escape to infinity, while the inner horizon marks the onset of more intricate causal and geometric effects, where classical determinism becomes subtle and spacetime can behave in ways that defy naive intuition. From a physical standpoint, however, charged black holes are almost certainly unrealizable in nature, because astrophysical processes rapidly neutralize any net electric charge. Any substantial charge on a black hole would attract opposite charges from the surrounding plasma, leading to discharge over extremely short timescales compared to the age of the universe. Nevertheless, the Reissner-Nordström solution remains invaluable as a theoretical laboratory. It allows physicists to explore how multiple horizons affect the structure of spacetime, the motion of particles near a black hole, and the extreme behaviors of gravity and causality in the presence of both mass and electromagnetic fields. The mathematics reveal that the horizons shift depending on the magnitude of the charge, approaching coincidence in the case of an extremal charged black hole, where the charge is equal in natural units to the mass. This extremal case presents a fascinating boundary condition in which the black hole's temperature approaches zero, and the classical singularity becomes hidden behind coinciding horizons, suggesting tantalizing connections to quantum gravity and string theory. The story of black holes takes an even more profound turn when quantum mechanics enters the picture. In the 1970s, Stephen Hawking revolutionized the field by showing that black holes are not entirely black, but emit radiation due to quantum effects near the horizon. This phenomenon arises because the vacuum of space is not truly empty. It is teeming with fluctuations, particle-antiparticle pairs that spontaneously appear and annihilate in accordance with the uncertainty principle. Near the horizon, these vacuum fluctuations interact with the extreme curvature of spacetime in such a way that one member of the pair can fall into the black hole while the other escapes to infinity. To a distant observer, this escaping particle appears as real radiation, meaning that the black hole is radiating energy, and over time, this radiation leads to a gradual decrease in the black hole's mass, a process known as black hole evaporation. Hawking derived a precise temperature for this radiation, which is inversely proportional to the mass of the black hole, expressed as T equals h bar c cubed over 8 pi g m k sub b, whereas the reduced Planck constant is the speed of light, is Newton's gravitational constant, is the black hole mass, and is Boltzmann's constant. This formula reveals a striking result. The smaller the black hole, the hotter it becomes, radiating more intensely, while massive stellar black holes have extremely low temperatures, far below the cosmic microwave background, and therefore evaporate extraordinarily slowly. For black holes with masses comparable to stars, the time required for evaporation exceeds the current age of the universe by many orders of magnitude, making the process essentially negligible on observable timescales. Yet the principle itself is revolutionary. It demonstrates that black holes are thermodynamic objects, possessing entropy, temperature, and the ability to exchange energy with their surroundings in a way consistent with the laws of quantum mechanics. The existence of Hawking radiation immediately raised profound questions about the nature of information in black holes. According to quantum mechanics, physical processes are unitary, meaning that information about the initial state of a system is never lost. Yet if a black hole evaporates purely thermally, radiating a spectrum that depends only on its mass, charge, and spin, the specific information about the matter that fell in seems to vanish from the universe. This conflict, known as the black hole information paradox, remains one of the deepest unsolved problems in theoretical physics. Does the radiation somehow encode the information in subtle correlations, or is information fundamentally destroyed, requiring a modification of quantum theory? Over decades, physicists have proposed numerous resolutions, including holographic principles, black hole complementarity, and ideas from string theory and quantum gravity. Yet a complete, experimentally verified solution remains elusive. Charged black holes provide a particularly fertile testing ground for these questions. The Reissner-Nordström geometry, with its multiple horizons, creates additional subtleties in the way quantum fields behave near the inner and outer boundaries. Hawking radiation may emerge primarily from the outer horizon, but the inner horizon introduces instabilities and potential amplification of quantum effects, affecting how information might propagate or be scrambled before reaching infinity. The interplay between charge, multiple horizons, and quantum field fluctuations suggests that even a theoretical black hole, far removed from astrophysical reality, can serve as a laboratory for understanding the deep connections between gravity, thermodynamics, and information theory. Evaporation of black holes through Hawking radiation also implies that over fantastically long timescales, all mass energy trapped in a black hole could be returned to the universe. This leads to an entirely new way of thinking about the life cycle of black holes. Rather than eternal sinks of matter and energy, they become temporary repositories whose energy gradually leaks back into the cosmos. For small, hypothetical primordial black holes, the evaporation process could be rapid enough to have observable consequences, including the emission of high-energy particles, gamma rays, or even bursts of radiation, as the final stages of evaporation accelerate dramatically. These possibilities tie black hole physics to cosmology, early universe physics, and searches for dark matter, suggesting that the study of charged and quantum black holes is not purely theoretical, but potentially observable. The combination of the Reissner-Nordström metric, Hawking radiation, and the associated information paradox shows that black holes are far more than simple gravitational traps. They are dynamic, quantum objects with complex causal structures, thermal properties, and implications for the ultimate fate of information and matter in the universe. Charge, rotation, and quantum effects together reveal the rich tapestry of possibilities predicted by combining general relativity and quantum mechanics. Even if astrophysical charged black holes are unlikely to exist, exploring them mathematically allows physicists to probe the limits of theory, to understand how horizons, quantum fields, and spacetime interact, and to confront the deepest questions about the nature of reality itself. In this sense, the study of charged black holes and Hawking radiation unites classical relativity with quantum physics, highlighting the duality of black holes as both simple, geometrical objects and complex, thermodynamic and quantum systems. They remind us that horizons are not mere boundaries, but sites where geometry, energy, and information converge in ways that defy everyday experience, and that the mysteries of black holes extend far beyond the event horizon into questions that touch the foundations of physics, the nature of space-time, and the ultimate limits of knowledge in our universe. Firewall hypothesis and real observations. The firewall hypothesis emerged in 2012 as a startling proposal to resolve a deep paradox at the intersection of quantum mechanics and general relativity, crystallized in what is known as the AMPS paradox, named after Almheiri, Marolf, Polchinski, and Sully. The paradox arises from the tension between two foundational principles of physics. On one hand, unitarity in quantum mechanics demands that information is never lost. The evolution of a closed system must be reversible, implying that any information swallowed by a black hole should somehow be recoverable. On the other hand, the equivalence principle of general relativity asserts that a freely falling observer crossing the event horizon should experience nothing unusual locally. The laws of physics in a small enough patch of space-time are indistinguishable from those in empty space, meaning the horizon should appear smooth and unremarkable. AMPS showed that if Hawking radiation is purely thermal and unitarity is preserved, then these two principles cannot both hold. Either information is destroyed, violating quantum mechanics, or the horizon is no longer smooth, violating general relativity. The firewall proposal resolves the paradox by suggesting that a searing wall of high-energy quanta exists at the event horizon. According to this idea, any infalling observer would be incinerated upon crossing, encountering violent energetic particles instead of a smooth passage through spacetime. In effect, the horizon becomes a literal firewall, rather than a benign geometric boundary. While this concept preserves unitarity and ensures that information is not lost in the radiation, it violates the equivalence principle, introducing a radical departure from Einstein's theory in a regime long assumed to be innocuous for free-falling observers. Despite its theoretical appeal in addressing the information paradox, the firewall hypothesis remains entirely untested experimentally, and no observation has yet confirmed or even suggested the existence of such extreme phenomena at black hole horizons. The discussion is purely theoretical, framed to reconcile the fundamental tension between quantum mechanics and general relativity, and it has sparked intense debate over the nature of space-time, information, and the ultimate fate of matter falling into black holes. While the firewall hypothesis remains speculative, real astrophysical observations have provided increasingly precise insights into black holes, giving context to these theoretical questions. Cygnus X1, one of the first strong black hole candidates discovered in the 1960s, offers compelling evidence for stellar mass black holes. Its X-ray emissions and binary dynamics demonstrate the presence of an unseen massive object so compact that no known mechanism other than a black hole can explain it, confirming decades of theoretical predictions about these objects. Observations of the motion of its companion star allowed astronomers to measure the mass and size constraints, establishing Cygnus X1 as a laboratory for studying extreme gravity and high-energy phenomena near a black hole. Sagittarius A star, the supermassive black hole at the center of the Milky Way, provides another observational anchor. Using decades of precise stellar orbit measurements, particularly by Andrea Ghez and Reinhard Genzel, astronomers mapped the motion of stars in the galactic center, revealing a concentrated mass of about 4 million solar masses confined to an extraordinarily small volume. These measurements confirmed the existence of a compact object whose gravitational influence dominates the surrounding region, consistent with the theoretical predictions for a supermassive black hole. The study of stellar dynamics around Sagittarius A star has allowed for increasingly precise tests of general relativity in strong field regimes, and has helped refine models of black hole horizons and accretion physics. The advent of the Event Horizon Telescope in 2019 provided a landmark achievement in observational black hole physics by producing the first image of the shadow of Messier 87, a supermassive black hole located in the Virgo A galaxy. This image does not capture the event horizon itself. Nothing can be observed directly at the horizon, but instead reveals the shadow created by light bending and capture near the photon sphere. The photon sphere, located at a radius approximately 1.5 times the Schwarzschild radius for a non-rotating black hole, is the region where photons can orbit the black hole, albeit in an unstable configuration. The shadow corresponds to the boundary of photon trajectories that spiral inward, silhouetted against the luminous emission from surrounding accretion material. This observational breakthrough provides direct empirical constraints on black hole mass, spin, and the structure of near-horizon spacetime, bridging the gap between theoretical models and observable phenomena, even as the detailed physics at or inside the horizon, including the potential existence of firewalls, remains inaccessible. Together, these observations, ranging from Cygnus X1 and Sagittarius A star to the Event Horizon Telescope, confirm the existence of the extreme compact objects predicted by general relativity, reveal the behavior of light near the photon sphere, and demonstrate that the gravitational influence of these objects matches theoretical expectations remarkably well. Yet they do not resolve the deep quantum questions encapsulated by the firewall hypothesis. The horizon remains fundamentally unobservable directly. Photons emitted from inside cannot escape, and the extreme curvature ensures that classical descriptions remain valid only up to the horizon itself. In this way, The theoretical speculation of firewalls exists alongside a growing body of empirical evidence describing the behavior of matter and radiation near black holes, highlighting the interface where quantum theory, relativity, and observation converge, and framing one of the most profound questions in modern physics. How do information, quantum fields, and the geometry of space-time coexist at the most extreme boundaries of the universe? The shadow is not the horizon. What we actually see when we look at a black hole is not the event horizon itself, but rather the complex interaction of light emitted from matter swirling around it, and the gravitational lensing imposed by the black hole's immense curvature of space-time. Photons emitted from the accretion disk, heated to millions of degrees as they spiral inward, are bent, twisted, and sometimes captured entirely by the black hole. The result is a dark silhouette surrounded by a luminous ring, the shadow. This shadow appears significantly larger than the true event horizon, with an apparent diameter roughly 2.6 times the Schwarzschild radius for a non-rotating black hole. The inflation of the shadow's size arises because photons that approach near the photon sphere, located at about 1.5 times the Schwarzschild radius, can orbit the black hole multiple times before escaping or falling in, creating a magnified silhouette that depends not on the horizon itself, but on the paths light can take around the gravitational well. The image produced by the Event Horizon Telescope for Messier 87 demonstrates this beautifully, revealing a sharp boundary in the emission of surrounding matter while leaving the actual null hypersurface of the horizon invisible to direct observation. Beyond these observational phenomena, it is essential to distinguish between the apparent horizon and the event horizon, concepts that are mathematically precise but physically subtle. The event horizon is a global, teleological feature. Its location depends on the entire future evolution of space-time. It is defined by null surfaces, light-like boundaries from which no signal can ever escape to future null infinity. The apparent horizon, in contrast, is defined locally at a given instant by the trapping of light rays. In dynamic situations such as during black hole mergers observed by LIGO, these horizons do not coincide perfectly. As two black holes spiral together, their horizons distort, stretch, and eventually merge, producing complex, evolving causal structures before settling into a single, final event horizon. Gravitational wave signals carry the imprint of this evolution, the so-called ring-down phase, providing direct observational access to the behavior of horizons in extreme, time-dependent scenarios. The strangeness of the event horizon becomes even more apparent when we consider hypothetical extremes. If the Earth were to fall into a stellar mass black hole, the infall would unfold differently depending on the frame of reference. To a distant observer, the fall seems to freeze near the horizon due to gravitational time dilation, while in the proper time of the infalling observer, the journey to the singularity occurs in a finite duration. Tidal forces near stellar black holes would stretch and compress matter, producing spaghettification, whereas supermassive black holes would allow a more gradual passage before extreme effects near the singularity. The same principles scale to primordial black holes, potentially formed in the early universe, where horizon sizes vary with mass and extreme gravitational effects manifest on correspondingly small or large scales. In all cases, the horizon remains a null hypersurface, a boundary defined by the causal structure of space-time rather than any solid or locally detectable material surface. Mathematically, the event horizon is a collection of null geodesics forming a light-like boundary. In Penrose diagrams, the horizon delineates the point beyond which all future directed paths inevitably lead inward toward the singularity, establishing a global causal structure in which the interior of the black hole is forever disconnected from the rest of the universe. Even though an infalling observer crosses this boundary without noticing any local change, the outside universe can never witness the crossing. The horizon traps light, bends space-time, and determines the ultimate fate of any matter or radiation that passes it, all while remaining invisible and intangible. Quantum effects, such as Hawking radiation, can slowly shrink this boundary, introducing subtle instability and suggesting that horizons are not only geometrically strange, but also subject to the principles of quantum mechanics. Current research pushes these concepts further into the frontier of physics. Quantum gravity theories propose that horizons have microstates that encode information, potentially resolving the black hole information paradox. Approaches from string theory and loop quantum gravity offer models in which the classical horizon is an emergent or coarse-grained feature of an underlying quantum structure. Observationally, gravitational wave astronomy provides a new avenue to probe horizon dynamics. The ring-down signals following black hole mergers test the predictions of the no-hair theorem and the stability of event horizons in real space-time. Future telescopes, including next-generation versions of the Event Horizon Telescope and space-based interferometers, promise increasingly precise imaging of accretion flows, shadows, and possibly even deviations from classical predictions, offering the prospect of constraining theories that link quantum mechanics and gravity. Ultimately, the event horizon is a null hypersurface in curved spacetime, a boundary defined purely by causal structure where the escape velocity equals the speed of light. Beyond this surface, all future directed paths inevitably move inward. It is strange because it is simultaneously undetectable locally, invisible, and yet measurable indirectly through its gravitational effects. Observers can cross it without noticing, while distant observers see nothing cross in finite coordinate time. Light is trapped, time dilates dramatically, and the classical boundary is subject to quantum effects that allow it to shrink slowly. The horizon's properties depend on the geometry of the entire future of spacetime, making it not a physical wall, but a profound feature of the universe's structure. It is this interplay of geometry, causality, relativity, and quantum mechanics that makes the event horizon one of the most extraordinary and counterintuitive objects in the cosmos, a surface that defines the ultimate limits of observation, motion, and information in the universe.